Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
Excellent. So our journey of remote sensing continues. Onwards and upwards, as they say. So we had our previous video tutorial, 1-to-1, that focused on geographically weighted regression models. So we generated, I think, 3 of them, if I'm correct, within RStudio. Then we generated the predicted values for each of those models, geographically weighted regression models, and then we rasterized it, and then we moved it into QGIS, blah, 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 blah. Okay, so we've done now the random forest one, we've done multiple regression time series, then we moved over to the spatial regression, and then we did the geographically weighted regression. So there's 4, call it classes, if you want to use that term, of regression models that we've done so far within RStudio. And remember, we generate the predicted images and we move it in QGIS. The idea is to generate a sample of these predicted values and then compare them. And for this, my region of interest and the NDVI variable, which one is superior, etc., etc., etc. So that's what we're doing at this stage. So just to show you quickly, just in QGIS, QGIS, we've done our random forest one, and then we did the multiple regression, the robust, and then I did all the other 1, 2, 3, 4, 5 time series regression models, which is the LMS, the LTS, the RSMM, and LAD. I'll quickly go through them. And then we did the spatial regression models. There is 1, 2, 3, 4, 5, 6 of the 7 of them. And then we did, there's the 3. There's the 3 geographically weighted models, predicted images. So we have a variety, quite a large diversity of regression models. So the one that we're going to focus on in this particular video tutorial is the support vector models, or support vector regression. Okay, there's 2 sites there that you can go and have a look at. And it's a class of, it's in general assumed, it's associated with land use, land cover classification. But we can also use it for regression. You can do your own homework, read up a little bit on support vector modeling. Again, there's quite a bit on the web on the modeling itself. So first of all, we generate our empty raster for our NDV. Remember, this is the empty raster that we're going to populate our predicted values in. Okay, so we run that. Okay, so we use our NDVI extent, this one here, with our X and Y coordinates, our original data. So that's going to create the extent for us. We populate the coordinates, we make the referencing system, the coordinate reference system, the 84, and we just add them together. So that creates our empty raster, but that raster has exactly the same extent as the, let's have a look there. If I do this, let's quickly just run it, see what happens if I do this. Let's look there, see there it is, our dimensions, resolution, extent, and our project. So that's an empty raster. It has no data. Okay, it has no data, but it has exactly the same extent, height, width, pixel size, etc., referencing system as our original NDVI raster. And that is what we're now going to use to populate our predicted values, or to rasterize it, so to speak. Okay. we've done those things a couple of times in our previous video tutorials. So that's sort of our standard issue. Then we generate our first support vector model or regression model. It's got that SVM. Ne? It's got that SVM. If we go to library, remember this is the library to run our support vector models in RStudio. E107. Don't ask who or why decided on that one, but anyway, that is it. Okay, so that's the library that you need to upload and install to run support vector modeling in RStudio. Let's quickly go where we will now. I keep on losing track. Okay. Where is it now? There we go. So let's run it. It's our standard model, our standard regression equation or standard equation using the NDVI original data set, okay, which has the NDVI value, the elevation value, the rain value, the temperature value, and the X and the Y coordinates. Okay, so we run that. Oops, sorry. I run it, and let's see what the model looks like. It tells you, there's the formula. It tells you it's a support vector model, and it's using an epsilon regression technique. Okay, you're using an epsilon regression technique. It's got a kernel, which is a radio kernel. It costs gamma and epsilon. These are parameters that it searches for. Number of support vectors, 4,137. Okay, so here we go. We can extract that support vectors, okay, from our model. Okay, so that's extracting the support vectors, okay, from our model. So that's our model, and then the $sign, and that is support vectors. We give it a name. You can give it any name, but that's how you extract the support vectors. Let's run it, and then let's display the support vectors. There it is. And basically, okay, so remember it's going to be 4,100. So they're only displaying the first 370. Omitted is 380. You take the 370 and add it, you get to that 4,100 and whatever the number is. We go up. So there we go. It is, where did it say now? Somewhere here. There we go, 4,173. So basically what the support vectors is, you see it's got for each of the explanatory variables, it has coefficients. You see, it's for each of these points, these locations, location 1, 2, 3, it generates coefficients. Remember our NDVI. So it generates this equation for each and every single location, okay, and that's what the support vectors are. Okay, then we generate the dual coefficients. Okay, so if we generate, you'll see the reason, because it's we're now interested in creating a weight for each of these ones. So there will be a weight for each of this one, and that weight will then determine the overall coefficients of the model. So the overall coefficients of the model, the overall elevation, rain, and temperature coefficients is based on these matrix or these individual coefficients multiplied by the weights. See, there's the weights, and then use that weights then to generate the overall coefficients. I hope that makes sense. Okay, so that's the coefficients, the support vectors for each location. And then by using the dual coefficients, you'll see the dual coefficients is just minus ones and ones, which we then will multiply. You see, plus 1,000 gives you 4,000. So it will take these dual coefficients, these minus ones and ones, and it will multiply it by the individual coefficients, and that will give us the weights. Okay, so let's do that. Let's see what that looks like. Let's see what that looks like. And there's our values, or our coefficients for the model as a whole. And I said these coefficients are generated by multiplying the individual coefficients times that the dual coefficient, which is just multiplied. And that gives us the overall. And there is our intercept as well. Okay, so let's print our, okay, so there's our model coefficients, and there's our intercept. Okay, and I said these ones are all based on the individual coefficients multiplied by each dual coefficients to get to what we call the weights. Okay, so that's just the same things, just different. You'll see it's the same coefficients, just calculated a little bit different, etc. Now what we can do is we can generate the predicted values, okay, and that will be based on these coefficients. So that coefficients will now go into the model, and that will be used then to generate our predicted values. So we run our predicted values, we can plot our predicted values. Let's click, there's our actual versus the predicted values and the actual values. We can add a linear function there towards that, etc., etc. But as I'm interested in generating a rasterized image of the predicted values, so we use our standard script that we used in most of the other modeling, other classes of regression. As I said, we generate our predicted values, which we've done. Then we add our predicted values, the coordinates, to our predicted values. Because remember, the predicted values are just the row with each predicted NDVI value, but it doesn't have the coordinates. So what we're doing now is we're adding the coordinates to that. So that okay, let's quickly just print it. I'll show you. If we just run that, you'll see now. If we run that now, you'll see that that's each predicted value. Okay, let's go up again. So each predicted value will have now an x and y coordinate. So that's what we've done there. Okay, here we just created this values, that one there, in the first column, in the first, this one, this code. We generate the predicted values, 0.35, 0.36. Then we add the x and y coordinates. And then we take this, now the x and y coordinates, and we impose it, or we input it into our blank raster. The one that we've created here. This one there, our raster template, you'll see there. We add that to our raster template. And then we just, and then we plot that. And then we plot it. And that's how it looks. And then we export it into our project folder. And then we export it to our project folder. And then it's in our project folder, and then we can upload it into our QGIS. Simple and straightforward as that. And so the methodology of the support vector is it generates a set of coefficients for each and every single point, and then it uses a weighting methodology to generate the overall coefficients for the model, for my region of interest. But we can go one step further. Remember, it's using a number of parameters. Let's quickly go there. You'll see if we generate the parameters of the model itself, you'll see that's the parameters that it generates. It uses epsilon regression type. It includes a radial kernel. It's got a cost and a gamma and an epsilon. Okay, so that's the parameters. We can change that. So that's by default. Okay, so that's by default. We can change those parameters to make the model either better or worse. So what we're going to do in the next one is we're going to try to improve on this. You'll see we'll say the type is the epsilon regression, similar. But what we then do is we don't use a radial kernel, we use a linear kernel. So we just amend the kernel. Okay, so let's run that. And then let's see what that parameters look like. You see the kernel is exactly the same. except the kernel is now linear, where this one were radial, and the other variables are exactly the same. It's slightly more support vectors. And then we do exactly the same as we did with the normal one. So we change the kernel to a linear kernel where the previous one was a radial kernel. Okay, so let's run that one. You can see all the stuff is already done there. So are you sure? So let's run it, and I want to get to the run. We're going to do that run. That's exactly the same as what we've done, and then I'm just going to plot. I'm going to plot it, and there it is. There's our predicted NDVI rasterized image based on the slightly amended support vector model irrigation equation where we use the kernel. So those are our two. We can change, yeah. So what we can further do with the support vector, it allows you to do some fine tuning. It allows you, the support vector model generates a whole lot of models itself, and then it compares each of these to generate the best fit model. So here we input the model details in the first two. In the third option, we allow the model to train itself, run a number of models to basically learn from itself, and then for each of these it generates the fitted values, and then it automatically then compares these fitted values, and it will then generate the best fit coefficients or the best fit models. Now this is the code. Okay, this is the code that we run. This is the model what we run eventually. Okay, there's the epsilon parameters, the cost parameters, etc. There is the training and the testing and all of these things. Now, I ran this, tried to run this on Friday. Today is Sunday. So I left it running for Friday night, for Saturday, and for Saturday night. And this morning, after 2 days, I eventually said, no, I'm not going to do it. I'm going to stop the running. So it was running for 2 days, and it was still operating. And that's just simply because I've got so many, as I said, my region of interest is quite big. I've got a huge amount of locations, point locations. So it's yeah, I couldn't get it to finish. So I've stopped it. Okay, but if I had a smaller region of interest with fewer points, then potentially you'll run this, and it will generate a best fit model itself. Okay, so it will keep on training and learning from itself until it generates a best fit model. And then the idea is to generate the rasterized image from this best fit model, and then, as I said, same things as previously, move it into QGIS. So I'm not going to run this because it said it will just take, again, another 2 or 3 days. But eventually we've got two support vector models. Okay, we've got 2 support vector models. And I have, okay, so let's quickly go to QGIS. So I am in QGIS, so I'm going to go to my layer. I'm going to go add layer. I'm going to go to raster, and let's import the 2 support vector models. So we're going to go add, and let's see where, okay, so there it is. Okay, so there is the one support vector model. Let's go and give it a single band, same as all the others, quantile, classify, and apply. That it is rasterized predicted image. And then the kernel one with the linear kernel, we go the same. We're going to go to single color. We're going to go to quantile, classify, and apply. And there it is. So that's the one. And this is the second one, and that's the original one. So let's quickly have a look and see what that looks like in terms of if we compare the values to the actual NDVI values. Let's choose a location. Let's have a look. That's the actual NDVI value, 0.47. Let's use our first one, 0.45, and our second one, 0.38. So that's actually much worse than our first support vector model. But as I said, it gives us a predicted image that we rasterize in RStudio. We bring it into our QGIS, and you can see now the list is starting to it's getting a lot. So there is prediction images for our NDVI predicted image for all of these models, for all of these regression models. And these regression models are quite diverse, it's quite different. So let's reserve judgment to say which one is best and which one is worst until we've done all our predicted models. Until we've done all our predicted models. It's a pity we cannot get the tuning. We cannot tune our support vector model to improve on it. When I said I've tried, it was running for 2 days. It just doesn't want to work. It just goes on and on and on and on and on. But one should be able to do this if you have a smaller region of interest and less point layers. Then we should be able to do that. But yeah, this is what the support vector machine model allows you. It allows you to generate best fit models, and it will do this automatically. It will learn from itself and continuously try to improve on it, and that's why it's taking so long, because it's running and learning and running and learning and improving and stuff. Yeah, so that is the support vector regression or support vector modeling within RStudio. It's another class of regression modeling, or another class of predictors for our NDVI, for our region of interest. And we'll see how it fits into the overall, call it accuracy classification. We'll see how it fits, whether it is worthwhile pursuing this. Okay, so that is support vector methodology. We're going to do, I think, one more, which is, I think we can also do random forest within RStudio, so we're going to do that. And then we're going to wrap on our regression models, and then we're going to go and do our prediction analysis to see which one actually is better, which is worse, etc., etc. Okay, so that's what we're going to do in the next video. We're going to continue with this, continue on this path until we have a winner. And by definition, if we have a winner, we must have a loser. But it would be interesting to see. Nonetheless, it would be interesting to see. So that's support vector regression or support vector modeling. And with that, let me park this. And thank you for thanks for joining me, and thanks for your support. I really appreciate it. Please remember to like, subscribe, very, very important, subscribe. If everybody that watches these videos subscribe, I will easily reach my target. So please, please, please like that, press that subscription button. It works, it does work. I watch those numbers on a daily basis, almost, more than a daily basis. Anyway, thanks a lot, and stay tuned. I shall be back, and as I always say, I'll see you on the other side.